My name is Shachar Shemesh. Believe me that in my native language, it's a very simple name to spell and to pronounce. And let's not talk about anything else now. This talk is about undefined behavior from the compiler's perspective. I'm now going to do my rendition of slide number 2. Slide number 2 is always titled, Who Am I? I figured the audience here can be divided into two groups, those who already know and those who don't care. Sorry, I meant, yeah, that's better. So let's talk about a more interesting subject. Let's talk about who you are. This talk is actually intended for two distinct audiences. One audience is those that would like to know more about undefined behavior, what it is, why it behaves the way it does, what makes people say, "Oh, it's dangerous, don't do that." I'm sorry about the audio rebalance. And the other, and to them, this talk is meant to say, be afraid. The other audience is those who already know what undefined behavior is, already know why it's dangerous and why people say not to use them. And to them, this talk is meant to say, you're overdoing it. People will use undefined behavior, and rightfully so. So, where did this talk start? It started with an example called square. The example itself, I'll give it to you, but it's not very interesting. What is interesting is where I found this example. This example came from a pool of interview questions. So there's a company that offers other companies a pool of interview questions to ask interviewees and have them answer. And it went, not this. It went something like this. So, can everyone see?
Except there's something on the
right.
spilling over.
I'll take care of that as soon as I manage to. Can everyone see now?
Yes. Yep.
Okay. Need bigger fonts? Okay. So we are talking about a program that looks something like this. We have a IO stream.
I cannot read that all. You have to increase the font size, please. That's better, thanks.
Okay. And it defines a macro, I'm sorry, I know, called square, that generally looks like this. They actually named the macro square. And then the main program defines a variable that names it 3. And then we print the square of var. And that prints.
Read.
Hopefully 9. Why can it?
Pseudo-vim.
Yeah, my prep work is interfering with my talk now. Okay. And now, I'm guessing you want larger fonts here as well. If we compile this, and we run, it prints 9, to everyone's complete and utter shock. But now they said, okay, what does this print? And how come I'm still here? I'm sorry about that. Right, so what does this print? And if you actually run it, it prints 25. Now, obviously, the purpose of whoever wrote this as an interview question was to say, oh, make sure that the interviewee knows that when you invoke a macro, it reevaluates the expression. So it increases var twice. But then the explanation needs to deal with the fact that it actually prints 25. And the explanation given there, because obviously it's a pool of questions, so they also give you the answer, was since the order of evaluation of arguments in C++ is implementation defined, it can either increase the first instance and then the other, or the other and then the first, which is why the answers are 20 or 25. And the thing about this explanation is that it is utterly wrong. And it's very easy to see that it is utterly wrong because multiplication is a commutative operator. So it doesn't matter if we multiply 4 by 5 or 5 by 4, the answer should have been 20. What's actually happening here is a combination of operator evaluation is indeed indeterminate, unsequenced, and we modify the same external variable in an unsequenced operation, and that's undefined behavior. So let's talk about undefined behavior. So I'll start off by saying that the terminology is a bit confusing. We have just behavior that is not defined. So any spec, no matter how carefully written, will have holes. And those holes are obviously not defined. And when a layman hears undefined behavior, typically that's what they'll think about. And for years I go and say at this point, but that's wrong. That's the wrong way to think about it. I am no longer sure that is an accurate statement. We'll get back to it. Then we have something called unspecified behavior. Now, I'm talking to a room, some of which are people who wrote those things. So I will tread very carefully and hope nobody throws any tomatoes. Unspecified behavior means the compiler is free to be expressive in exactly how to take the definition and turn it into code. It can play around a bit. Do it sometimes this way, sometimes that way. I'm doing okay?
Yeah.
Okay. Then there's implementation-defined behavior. Implementation-defined behavior, unlike unspecified behavior, means that the compiler is still free to choose how it does it, but once it has chosen, it needs to be consistent.
I think there is another different. I think the implementation-defined behavior has to be documented as well.
Right. And part of that, it also has to be documented. Though as a programmer, as a user of the language, that's not really helpful to me because unless you write code that is meant to be compiled on a very specific instance, that doesn't create that much of a difference for me as a user of the language. And none of those is what we usually refer to as undefined behavior. So what is undefined behavior? That's simple. It's behavior upon use of a non-portable or erroneous program construct or of an enormous data for which this international standard imposes no requirements. Simple, right? We're done. Okay, we can go. Put another way, the moment the compiler is free to assume that undefined behavior never happens. Why? Well, two reasons. One of them is that it aids in optimization. So another one example that came up here before the talk, someone wrote code, it didn't help, didn't work. They added a print, and the print made the code work. Why? Because the print sort of creates a sequence. But this sequence isn't complete. So a function call to an external function that the compiler cannot see or decides not to look into splits the function into before and after. And there's a limit to what can move between them. But this limit is not absolute. Some stuff can move before and after the function call if the optimizer needs to. How? Because the optimizer is allowed to assume that local variables are not, that you have not given anyone else a pointer to, are not changed outside of the function. The compiler is allowed to assume that, and that allows the compiler to move stuff around function calls. So that's an undefined behavior. What happens if you do some black magic trick and change a variable, a local variable outside of the function? The code won't work. How will it not work? Not clear, right? So that's the idea of why undefined behavior. But the extent of unclear, I think, it needs some example. So I'm giving here an example. Unfortunately, it's not my example. I read it online. I don't know who made it because I would really like to buy them a beer. And I don't remember that example. I don't think that example had a name to begin with. I'm calling it Chekhov's gun. But if you do recognize it and know who wrote it, who originally came up with it, please do let me know. So this is how it looks. First of all, just an include for us to be able to see some output. And now we want to define a function. This is an evil function. For example, let's say it erases my hard disk. I don't want to actually erase my hard disk for reasons that I'll get back to later. But instead, I'll just print that I did. And I promise to return something. And one more thing. No, sorry, that doesn't matter. And now I want a pointer to a function with the same signature. Everybody knows how to create such a thing? Simplest way, copy the declaration and then add an asterisk next to the name. But of course, we can't call it evil. Let's call it fire. And one more thing, it's static. So it's only visible within this compilation unit. And then we want another function, load gun, because we called it a gun. And what this function does is it assigns evil to the pointer. And this function is not static. However, we offset it by never calling it. What we do call, however, is fire. And I have to take the jacket off. And the question is, what does this program do?
Seg v because fire is null.
So fire is a static variable. Static variables that are not explicitly initialized and don't have a constructor are a zero initialized. So yeah, fire is null. Let's run it. It crashes. It shouldn't surprise us, right? Let's make a small, tiny change to the command line. Let's add optimizations. I know, it's a great example. I really wish I knew who wrote it. Okay. So we understood that UBs is undefined behaviors, right? UBs can be problematic. What are they good for? So I mentioned before that they open up options for optimizations that we wouldn't otherwise have.
Are you going to explain a bit more about what we just saw? Or
I will circle back to this example. But another point I want to raise is that UBs are pretty much unavoidable in any language that is similar enough to C++. And to prove that point, let's write our own programming language, right? We'll call it C++ now 2025. We'll publish it in a book called the C++ 2025 Programming Language. And we're writing it. We can do anything we want here. We just want two basic guidelines. We want this language to have pointers and nullable pointers in particular. And we want this language to be performance-oriented over safety-oriented. So those are the two. So it can't be Java. It has to be a language that, in that sense, behaves similarly to C and C++. And at some point, we need to address the question, what happens if the programmer dereferences a null pointer, right? If we have nullable pointers, what happens? And we want to define that, right? We want a language with no undefined behaviors. So what should it do? Crash, excellent. Null pointer dereference crashes the program. Except this is the program, right? So first thing the program does is install a crash handler. And then in the crash handler, I exit. And now the compiler is obligated by our definition of the language to not compile this program because in this program, null pointer dereference does not crash. Right? The language requires that a null pointer dereference crashes, and this program does not crash on the null pointer dereference. Yeah.
Can you get around that? You're saying the definition that it sends the signal, the segfault signal?
Oh, okay, let's do that. No, I'm cool. You surprised me a little, but yeah, I'll go with the flow. But then what happens with this program? So first thing it does is it maps the first memory page of the program, of the address space, so that accessing it does not create a segfault. Now, technically, this won't run on Linux. The mmap will fail. But we have had kernel-level crashes that as kernel-level security vulnerabilities that as part of what they did made sure that the zero page was accessible so it does not crash.
You can do it with, there's some kernel options or something. We had a customer who did exactly that, made it work.
Right.
Yeah.
And the question is, if we codify that into the language, then the compiler is obligated to not allow this. Yeah.
So what if we specify that a null pointer access is an ordinary memory access, and then it is platform specified whether that ordinary memory access traps or not?
Okay, but then, so you could do that, and in a way, I'm arguing that we should do that, but still, the behavior of the program is undefined under that. right? You're not saying what will actually happen. And we know that null pointer accesses are the simpler case. We have uninitialized pointer accesses, we have array bounds violation. And the thing is, the point I'm trying to make here is that it is impossible for any language standard to dictate precisely what will happen under those circumstances. It has to say, you know what, you did that, you're off the reservation. You lost all right to complain to the compiler that it generated code that is different than what I expected it to do. So what I'm saying is, UBs are a necessary evil. But we can notice that all of our strangeness started when we introduced the optimizer. So the next question is, what is an optimizer? Okay, what does an optimizer actually do? And for the next few minutes, I'm not talking about UBs. I'm talking simply about optimizers. So I have a program here, which yes, thank you. Can everyone see? Okay, so the code initializes a variable to 42 and then just returns it. Not a very complicated program. And we kind of expect the compiled code to just return 42, right? Why not? And that's not what it does. However, it's not what it does because now I'm not sure where unless I turn on optimizations, in which case that's exactly what it does. So the question is how to get from this to that. And to do that, I'm going to invent my own machine language. Does anyone here not know what an intermediate representation is? So I'm basing this very loosely on LLVM-IR. LLVM-IR looks like this. But I'll use my own because I want it simpler to see. Okay, so this is our intermediate representation, or machine language, whatever. We made the language up. So some rules. First of all, each temporary, if you will, each value we generate as part of the execution is stored in a, let's call it a variable with a number. So 1, 2, 3, 4. And those are called single statement assignments. So they get a value once, and that's it. That value never changes. So it doesn't matter where in this function I reference %2, we're always talking about that specific value of 42. Okay? So that's rule number 1. And then what we see here is the breakdown of our program. We create a frame, and that's necessary if we have any local variable. And then, because everybody know what a frame is? I'll take that as a yes and go on. And then we allocate room for our variable. and we create the immediate 42. So %1 is the address of our variable, %2 is the immediate 42, and then we store %2 into the pointer referenced by %1. So we assign 42 to the variable, and then we load. So that takes care of the first line, the line that says int var equals 42. And now we need the second line that says return var. So we load the value from that same variable, and that's %3, and that's what we return from the function. So that's a simple, very narrow view of turning the C code or the C++ code I wrote into some intermediate representation. And the reason that's important is because you need some way to do that. You cannot eat the whole thing immediately. You need to break it down and handle it in smaller chunks. So that's the first step. And it's also the first step if we go back to the Compiler Explorer image. It's almost identical. And if I remove the emit LLVM, here's the creation of the frame. Here's the storing of the 42 into the variable. Here's the loading of the 42, and it loads into EAX, so that's the return. So that's how the code looks without optimization. But now we want to start optimizing, which means we need to get rid of something here. What can we get rid of?
Everything.
Okay, what's your reasoning for getting rid of everything?
You can just immediately move the integer into the return
Why?
position.
You need a reasoning. You need a rule that you can give the compiler to say, you can remove everything because.
We can look for pairs of store and load.
But the local variable doesn't have a lifetime outside the function that's otherwise untouched. So
Of course it's touched. Look, we store into it and then we load from it.
Other than by that load and store.
Right. So the very first step we do is to notice that in this line, we store to a variable. Sorry. Yeah, in this line, we store to a variable. And then in this line, we load from that variable. And because it is undefined behavior for this variable to change outside of our code, we are allowed to assume that the value we load into the %3 is the same value we stored in %2, which means that we can get rid of this line. We can simply return %2, which makes the program look like this. But now we see that we store a value into the variable that %1 has, and we never read it. We were reading it just a second ago. We could not have done this optimization step in the prior step. It would have been incorrect. But in this step, it is correct because we no longer read, we forgot we ever did. And now we can say, fine, we're storing a value into a variable and we never read it past that point. So this store can go. Do you see that? And now we notice that we're allocating a variable, but never use it. That wasn't the case in the previous step. We were using it. But after that optimization, we are no longer using that variable. So, well, if we allocate a variable and we're not using it, obviously we can just not allocate it. So this line can go. And now we notice that we're creating a frame in a function that has no local variables. Again, we could not have done this optimization in the previous step. But now this line can go. And what we're left with is exactly the function we wanted to be left with. We're left with return 42. But what you'll notice is that we did it with a series of optimization steps where each one was very small. It had a very specific rule that is easy to verify. It's easy to verify that if you allocate a variable and you never touch it, a local variable with lifetime that is limited to that function, and you never see anyone doing anything with it, then you can just not allocate it. I think everyone here understands that this rule is generally correct, not only for this function. And this process of optimizing by iteratively reducing the code with transformations we can prove are correct, it's called peephole optimization. But what you'll also notice is we had to invoke undefined behavior rules in order to do those optimizations. So we did those optimizations under the assumption that certain things that technically could be coded will not happen. And we needed those. If we need to assume that code outside of this function can touch local variables, we couldn't do the first step. And without it, we couldn't do any of the steps. We could not optimize that function if we did not have undefined behavior. Is that a stunned silence, or are we?
Well, so I'll bite. So when you could look at that code, how would something from outside of that function modify that variable?
I can guess the pointer. Maybe you gave me a pointer to another local variable, and I know what the offset is. Maybe I can switch you out in the context switch and read the stack pointer.
Okay, so like really, tampering with.
I'm doing bad stuff.
You've really voided your warranty at this point.
Yes. Okay. So that's a very good point. I'm doing stuff that is obvious to any reasonable programmer is avoiding the warranty, right? Which did not stop me being asked in a code interview what happens when you take a pointer to class A and move it to something which is kind of related but not really, and they wanted the full memory layout that resulted. So some people don't think of it as that much of a bad behavior.
You're saying it's an extreme example of more reasonable, common kind of behavior.
Right. And that is actually the point which you will see because we're now analyzing the Chekhov's gun example. The Chekhov's gun example is based on something called devirtualization. It was this one, right? So, what is the devirtualization? Devirtualization is under the assumption that virtual function calls are slower than concrete function calls, which we all know is true, right? At least you didn't see my talk called Optimizing Away Virtual Functions May Be Pointless. Yeah, I like to live on the edge. So devirtualizing a function call means that we take a function call that is indirect and try to, at compile time, reason about what it could possibly be calling, and then calling that as a concrete function call. So your source code says virtual function call, but the assembly says concrete function call. And the way you can do that is if you analyze anyone that might call this, trigger this, anyone that might be the destination of this virtual function call, and come to the conclusion that there is only one option. 0, you can do that. 5, you can do that. Only if the answer is 1. So let's see what happens here. We have fire, which is a pointer to a function, and it is static. When I said it was static, I said it was important. Because since it is static, the compiler says, I can reason about who writes to it. Nobody outside of this translation unit will write to that pointer. Cool. Then you have load gun. And load gun is non-static, which means that, and again, that's important, which means the compiler says, I cannot reason about who may or may not call load gun. I don't know whether it was called. What the compiler does know is that load gun is the only place where the fire pointer is initialized. So when we call fire in main, there are only two options. One, somebody outside of this translation unit called load gun, and now fire points at evil. And two, nobody outside of this translation unit called load gun, and fire is null. So two options. However, one of them means we're dereferencing a null pointer. And the compiler is allowed to assume that we never dereference a null pointer, which means the compiler is allowed to disregard that option. I know you're not calling a fire without initializing it first. I know it in my gut, and therefore I assume you didn't. And therefore, the only option is that somebody called load gun and fire points to evil, in which case I'll devirtualize the call and just call evil directly. Which is an optimization. We didn't expect it in this particular case, but at least it has a reason.
I think I would prefer it if the compiler didn't do that optimization.
I'll get to that. I'll get to that in just a bit. The thing to note is that null pointer dereference doesn't always look like a null pointer dereference. That's the problem here, right? That's the reason we looked at it and said, oh, what happened? I have actually even more pointed example, but that will wait for a moment. Before that, let me talk about a couple of real-world examples. And again, the context with which I came upon those is important. Because when I say real world, I mean I worked at a place and on two different occasions, an engineer would come to me and says, I have no idea what's going on here. What is this? So it's real world in the sense that people wrote this code. The first is the company produces a custom chip with a CPU on it, and CPUs need clock. And the way to generate clock is with a component called PLL. PLL is a component where you put in one clock at one frequency and it outputs a clock in a different frequency. And they're configured with certain variables. So this function was meant to calculate what is the values with which to initialize the PLL. And the thing is, it was compiled, it's written in C, and then it is compiled with some compiler into assembly or into machine language. And then it is not run on a CPU because the CPU is on a chip that was not manufactured yet. It was run in a Verilog simulator. So it's a simulator that simulates all of the transistors, and you get about 1 hour per millisecond, something like that. So simulating 1 millisecond of real time takes about 1 hour. But you get full access to everything, registers, everything. And what the engineer saw was that the wrong values were initialized in the PLL. And he came to me and we realized two things. First of all, this function was executed at compile time. So the parameters were known at compile time, and the compiler inlined everything and just ran with the result. Anyone see the undefined behavior?
Line 6.
Line 6, correct. Param 2 was 1. It's a division by 0. But I think we all understand that if we divide by 0, then interesting things will happen. What I think is less clear to me is why would a compiler run this code at compile time and not complain? That's what I'm less clear on. But again, it's a real world, well, the code itself was massaged a little to make it simpler but it's a real world example. The other real world example again, from the same project, again, I massaged the code a little bit, but that's the code. But the symptoms were this. Oh God. Okay, man said, okay, this is the function. I run it, and the assert on line 6 triggers. I print the value. It's less than 32 and more than 0. So the value is 5, something like that. And yet assert number 6 triggers. So I said, fine. Well, the assert mistriggers, but I know it mistriggers, so I'll remove it. And then the assert on line 5 triggered, which means we have a value that is simultaneously more than 32 and less than 0. And then I remove the assert on line 5. Anybody want to guess? And the compiler, yeah.
I'm not sure what you're asking, but is the UB the shift amount?
No, I'm not asking I'm asking what the compiler did when we removed the assert on line 5.
Meaning that both asserts are gone now.
Yeah. The compiler produced the symbol for GPIO set, but produced no code, which meant that when you took the pointer to this function and called it, another function was called. What's the UB? Calc data address dereferences its second argument. And what I want you to notice is how far away the actual UB is from the observed symptoms. It's not, oh, okay, I have something wrong on line 6. No, line 6 is totally fine. The UB is in another function, but it got inlined. So we've got an observability into it. And you can stare at this function for hours and not find it because it's not here. And also what the compiler did with it. How can you put out a symbol that doesn't point to anything and not write a warning? But the C++ standard allows it because let's roll back the logic here, okay? The only side effect this function has before the UB is on mGPIO outputs, and that's just a variable. So any side effects of that as side effects will only manifest themselves after the UB, which means the compiler is allowed to say, never mind. So line 15 goes, right? It's a register access. It dereferences a volatile pointer, but it's after the UB, so it's fine not to do it. So line 15 goes, line 13 goes because the null pointer dereference is pretty much at the beginning. And then we begin that same logic we did of removing operations that are no longer needed, right? So we're writing to mGPIO outputs, but nobody we care about will ever read it. So remove the write. And now we're initializing a local variable, but nobody ever accesses it, so remove it. And now we get to the assert. So there are two options, right? GPIO is more than 32, in which case we crash the program, or GPIO is less than 32, in which case we do not care what the program does. So we leave crashing the program in, but we remove the condition, and we unconditionally crash the program. And now when we remove line 6, the same logic moves up one line to line 5. And now when we remove it, it no longer matters what the function does if it's called. So it has no code. And yes, another function gets triggered, but yeah, it's undefined behavior, so that's fine. I'm guessing you're all okay with this now, right? Yeah.
So you said that the compiler can delete line 15 because it happens after the UB.
Yeah.
So what I don't understand is what are the requirements on the compiler if you do something before the UB? Because isn't the program's entire behavior undefined if there's a single UB? So then theoretically, even if it happened before the
okay, so technically, the compiler is not allowed to change the behavior of the program before the UB is triggered. However, this is not, as far as the compiler is concerned, this is not changing the program's behavior before the UB is triggered, because it's just a write to a variable. Who cares? It's not volatile, it's not anything. So long as you don't read it somewhere that matters, and nothing after the UB matters.
But before the UB does matter, that's what I didn't.
Yes, but just like in the return 42 examples, we could remove stores that didn't matter. That's exactly what we're doing here. We're removing stores that don't matter.
Yeah, I just want to say, in case this function ever gets called, it will eventually come to line 13, and then everything before that happens.
Unless the assert triggers.
Yeah, okay, but yeah,
that's why you can't optimize away the assert, because it has an observable side effect before the UB.
No, I understand that. I didn't know that the compiler has to preserve behavior before the UB. That's what I didn't understand.
Well, it does, but like we see, that doesn't mean what you think it means.
Wait, is it? I'm confused now. So is it has to preserve the behavior before, or
in this example,
it can do.
I'm saying in another.
It has to preserve the behavior before the UB.
Okay.
But it does not have to preserve the code. So if it can reason that the code has no effect, it can remove it, or at least no effect that will be observable before the UB.
But your statement was if there's any undefined behavior, then the whole program is undefined.
Right. So that was what I thought, but
that's not true.
That's correct.
That is correct.
That is correct. Any undefined behavior makes your program undefined.
But
it sounds like.
Well, it makes your program ill-formed.
No. UB is a runtime property. Ill-formed is a static property.
In C++, time travel is allowed through undefined behavior. You can propagate backwards. In C, it's not recommended, but in C++, it's fully allowed.
Considering who said that, I'm not going to argue. So.
To answer your earlier question about are we okay with this, as somebody works for a company that makes a debugger, I'm totally okay with this.
Debuggers act. Okay, I did waveform debugging. Waveform debugging is when you try to debug a program from the waveform of the simulation of the CPU it is running on. And if you stored the correct, if you made sure the correct values are stored in the simulation waveform, it's an amazing way to debug because you can have unlimited backward ability. You have unlimited ability to go backward in time and test what happened before. It costs you 1 hour per millisecond, but
we can do that with any design.
Yeah. I'm guessing not on embedded code that runs on FP and RISC-V.
Correct. Not there.
So another case often made, and again, not one I particularly agree with, is the signed int overflow. So if we take this, what we have is a loop that waits until a sum of something reaches 5,000, doesn't matter. And then we have a param where we keep incrementing it. And what we do is, if we're before we param past 10, we call option 1. And if after, we call option 2. Now, as far as machine language representation, doing this like it is written is suboptimal, because you have a branch inside the loop, and branches are expensive. What would be better is to split it into 2 loops, one for the until param reaches 10, and then the other for the rest of the loop. But you can only do that if you know for a fact that once param reaches 10, it will never go back. Now, as programmers, this seems obvious to us, but a compiler has to consider the possibility that there's an overflow. And as a programmer, you can reason, you say, well, I know pretty much, more or less, how much func1, func2 add, and there's no way we'll execute this code 4 billion or 16 quastillion or whatever times that will require for param to overflow. But the compiler cannot know that. And if we know param doesn't overflow, or if we know param is overflowing, is undefined behavior, we can do better optimizations. You had a question?
No.
No, okay. The thing is, I think these cases are not very common outside of high performance computing and high frequency trading. I think saying, okay, this is a good idea because this allows this for optimization that for over 90% of the population doesn't matter is the wrong solution. I think there are better options. Okay, we talked about that. Right, sorry. Even the Chekhov's gun example could have been the correct optimization if we had a second file. So we're not touching the first file, but we have a second file that has a global variable with a constructor that calls load gun. And that happens before main, and that would result in the fire pointer being initialized at the point we called it, and the devirtualization optimization doing the correct thing. So a lot of those cases, even when we see things we don't want to happen, are still legitimate optimizations given the premise, which is you're allowed to assume undefined behavior never happens. And the thing is, like we've seen with the integer accessing local variables from outside the function, it's kind of hard to put the line, to draw the line, to say, okay, yeah, we want the compiler to do this, but we don't want the compiler to do that. That's taking it too far. However, I would argue that where C++ draws this line is not the correct place. And I would argue this through 3 snapshots from a website I very hope you're familiar with, called CPP reference. And those are Bitcast, which is a library function that you give it a value and it gives you the same bits as another value with a copy. And a start lifetime as, which sort of does the same thing without the copy. and Lander, on which someone said there are 5 people in the world who understand this, and they're the only one who needs to know what this does. Because I'm going to make a claim that I think will be controversial. All those 3 are actually reinterpret cast. And the reason we have them and not reinterpret cast is because, well, there are 2 reasons. One I think is if that was the main reason, we could have done something about it. You can't use a reinterpret cast in const expert. You can't use reinterpret cast in compiler, in code that is run by the compiler. And like I said, if that was the only reason, I think we could reason about that and do something about it. The main reason is that it's hard to reason about what undefined behavior reinterpret cast creates. And so all 3 of those are intended at making sure the compiler knows what undefined behavior is okay and what isn't. They do not, by the way, remove the undefined behavior. The undefined behavior is still there. All the cases that you intuitively say, well, if you do that with reinterpret cast, obviously will you result in undefined behavior, will still result in undefined behavior here. So yeah, okay. Here's the thing though. Like I said before, null pointer dereference doesn't always look like a null pointer dereference. And before offset off was introduced to the language, let me just go on record here and say that I do not think introducing offset off to the language was a mistake. I think it was a good idea. But before it was introduced to the language, this was the way you did offset off. You used a macro, and in the macro you got a type and a member, and then you cast null pointer to be a pointer to the type. You looked at the member of that type and you took the address of it. And that gave you the address of the member if the type begins at address 0, which is the offset of the member into the type. But that's undefined behavior. Just a second, okay? That's undefined behavior because as far as C++ is concerned, this is a dereference. This arrow operator is a dereference, even though we're immediately taking the address, so the compiler does not actually generate access to that address. With minor caveat, if T is a type that has a virtual inheritance somewhere in its hierarchy, and M is in that virtually inherited base class, then you do in fact need to dereference the pointer and offset off the keyword actually detects that and errors out, which the macro can't. But which is part of the reason why I say I think introducing offset off into the language was okay. It was not a mistake. But for types, usually you write that out yourself. No standard library offered that macro. And for types where that is useful, you usually knew that there were no virtual addresses. And at first it worked. And then the compiler would start issuing warnings. They would warn about this. They wouldn't warn about the other. Never mind. Would start issuing warning, look, you're dereferencing a null pointer. Go, yeah, not. And then offset off was introduced and solved the problem, assuming you want a standard pointer and not a pointer to member, which is still an unsolved problem to this day. You had a question. You
mentioned the standard offset of. Is it not just implemented the way that you should?
No, it's a built-in. It's a compiler built-in.
Ah, okay.
Because there is no way to implement it otherwise. Yeah.
So one thing interesting about the code on that last slide. So the standard doesn't say anything about what would be the representation of null pointer, right? This is assumption that it's all zeros. It's something that's like only the platform, like the platform defines offset offs, something like that. It may assume that, but the user couldn't like write that portably, right?
Right. So I also wanted to talk about argument evaluation order. Argument evaluation order is an artifact of a time where we had very few very few registers. So parameters were passed on the stack. And because we have very few registers, there was no way to store intermediate values. So the order of evaluation was the same as the order of pushing to the stack, the order the arguments were passed. And in C, very smartly, those were reversed from your intuition. Those were right to left, so that you can do something like printf, where the first argument tells you how many other arguments there are. So the standard said, well, I'm not going to say they're evaluated from right to left. I'm just going to say do whatever. And then we got the square example where that turns into an undefined behavior. And maybe we can move that past that point by now. And the same for null pointer. And I don't remember whether it was accepted that you're allowed to assume that integers are signed integers are 2's complement.
Nowadays you can.
Right. I think that's a move in the right direction. I think that because most code, even if I don't do this, which is very overt, right? But if I leave a pointer as a static variable, it will get initialized by 0 bits. And I kind of assume that's a null. So that creeps into the code anywhere. And at this point, C++ can either say, yeah, but that you're not allowed to, or it can say, yeah, do we really need this still, 2025? I had the same about I don't remember which one of the 3 library functions I put up. On one of them, I remember someone on the list saying, or even in the formal request for change, they said, I've never ran about, of course, any case where that actually caused problems. But potentially, reinterpret cast is always an undefined behavior. So anyone needs more info about this? There's something called intrusive structures, intrusive linked list, intrusive PTR. What the idea is, if you have, for example, a reference counted pointer, smart pointer that is reference counted, you need somewhere to store the reference count. Now, the standard way is to do a double allocation. So you allocate the reference count and you allocate the actual struct. And then if you know you're allocating them together, you can kind of put them in the same memory. But a much, much, much better way is if the type knows that it is being reference counted and just embeds the counter into the type itself. That is called intrusive reference counting. And the thing about it, intrusive reference counting is the fastest performance-wise way of doing reference counting. Plus, it has the amazing property that you can take a dump pointer to this type and convert it to a smart pointer. So you can take a dump pointer to a type, and because it is intrusive and you know where the counter is, you can turn it into a pointer, smart pointer that tracks the lifetime and reserves the use. So it's a really useful element. And a similar element is the intrusive linked list. So again, you store the node that links back and forth, as part of the type. But if you want that as a generic library, the pointer needs to know where the member is that is the node. And the best way to do that is by giving it a compile time option that says where it is. But now, if the node links to the other node and not to the type, which you kind of need in order to avoid circular dependencies on the type, then you have a pointer to the node, and you need from that a pointer to the type that contains it, which is, you need offset off. But offset off not on static types, but on a pointer to member. Now, between you and me, if you reinterpret cast the offset to an integer type, that's what's going to be there, unless virtual base class, which we agreed doesn't work anyway. But that's very, very implementation defined, and way worse than having some offset off. So I could write a proposal. I have zero time. I could write a proposal saying, let's do an offset off that accepts only one parameter, which is of type offset, pointer to member, and returns the offset into the type. But it will take, even if I do write it today, it will take several years until it's in. And it would be nice to be able to use some macro in the interim. But I can't because it's undefined behavior. But at least we know what the UBs are, right? I mean, yeah. So there's no comprehensive list. If you go to Wikipedia and ask, what is undefined behavior in C++? They say, oh, undefined behavior in C++ is when compiler doesn't have any commitment about the code produced, like null pointer dereference and signed integer overflow. We cannot have a comprehensive list because we define any not defined behavior as undefined behavior. So the compiler is allowed to assume that your code will not do anything that the standard doesn't cover. So a comprehensive list is impossible. But, and that's kind of the point. Sometimes you kind of have no choice. You do some corner cases. You kind of just do it and hope everything will be okay. But at least we can, well, obviously not those on point number 2, but at least the rest we can search the standard, right? We can search the standard for undefined behavior. Except sometimes it appears as the behavior of the program is undefined. Sometimes undefined appears, but is not for undefined behavior. Behavior as undefined will find most. I don't remember this version of the standard this was searched on, but sometimes the standard can't seem to keep them straight. It says, then the behavior is either unspecified or undefined. I'm sorry, what does that mean? It means undefined. Who is it that is supposed to select whether it's unspecified or undefined? It's the compiler, right? So the user has to assume that it's undefined because that's the worst case. We have ill-formed too, which essentially says the same thing. Ill-formed does not always mean compiler error. So how can we make things better? It boils down to this. the first part of the talk, I said that UBs are a necessary evil. This is the part where I say UBs are a necessary evil. We should stop treating UBs as optimization opportunities and start treating them as programmer landmine. Language. Reconsider UBs. Removing UB from the language is the easiest thing in the world because unlike any other change we do in the standard, we do not have to consider backward compatibility. If something is UB in C++26 and we turn it into not UB in C++29, nobody can complain, hey, I was banking on the behavior here being undefined. What did you do? It broke my program. And think twice before we introduce new UBs. Please. Please. It's a very confusing subject for novices to comprehend. And I started out by saying that I used to think that the notion that undefined behavior is just behavior that is not defined, I used to think that it was a wrong notion. And I don't think that anymore. I think it's spot on. It's just that the implication of what that means are what most programmers, unless they have a lot of scars from past bugs they had to deal with, don't think about. They reach far outside of where your actual misbehavior is. They're hard to debug. And the other thing is for the compilers. I want to show you something. So, we compiled square and it just printed the 25. But I'm going to do a very, very small change to the command line. Okay? Very, very small. And it says, well, the warning is unreadable, right? Multiple unsequenced modification to var. What? Why? What does that even mean? But it prints, it says you did something wrong. It knew, GCC knew we did something wrong. It just didn't say anything. And what's more, once it knows we did something wrong, it prints the value we would expect it to print. It says, fine, you do you. I won't intentionally trip you up. And I think we need more of that. Because remember the PLL example? That was UB that was triggered in compile time executed code. There is no way the compiler didn't know there was a UB there. There was no way the compiler didn't know we were dividing by 0. And if it just said, did you notice you were dividing by 0 here? And then produce the same code. That engineer wouldn't have had to seek me out.
I'd go further. I'd just have it not compile. I think it should not compile and go further than what you're saying. I think in that case it should say, yeah.
Well, that would be a breaking change, right? But simply outputting a warning, there's no excuse why it doesn't do that.
This is very philosophical and maybe on my pay grade. But so if it's undefined, if it's defined that it will compile, if it's just undefined, what will happen? It's just refusing to compile will be outside of the.
You could make this not compile with W error though. Like you could have that behavior.
Yeah, but it's the thing. I mean, it's the old thing. So I think Rust is safe by default, defined by default, and C++ is undefined by default. It's like I'd rather see a lot of the things be more opt. If I really want those optimizations, like let me opt in.
That's the other thing. I'm guessing that's what Ben was about to say. We need a way to say, okay, there's a huge performance gain I can get here by assuming that signed overflow integers or unsigned overflow integers do not overflow. Let me explicitly turn it on for a specific use case. Here it will be a huge boon. Let me turn it on here and not bite me in the ass somewhere else. You had something else you wanted to say?
I wanted to ask, what's the default standard that GCC is using to compile? Because the fact that it produces 25 indicates that it's actually interleaving the evaluation of the arguments to multiply.
No, it pushes it to the beginning.
It must be interleaving them because the arguments to multiply would otherwise come out as 4 and 3.
No, it did both increments before the evaluation began.
Exactly. It's interleaving the evaluation of the arguments to multiply.
Okay, I have no idea why that means that, but fine, okay. So
am I?
Yes.
So
first incrementing 2 times.
And that's not allowed in 17.
It increments twice and then reads twice.
Yeah.
Right. So I'm wondering if GCC is just, if I'm right, if I'm wrong, if GCC is trying to be helpful in some way by making it 25, I don't know.
You want me to compile with 17?
Well, it's undefined behavior either way, so it's 25 is fine, but I'm wondering what
for
GCC,
some definition of
why
fine.
GCC is choosing to go down that route.
Is it possible that the pre-increment is actually grabbing an L value and then it increments the L value twice and it has 2 references to that same L value, which are now both 5?
I wanted to point out something which you may have missed. This is compiled without optimization. I think GCC just does all of the side effects at the beginning of the evaluation of the expression. So it does all of the side effects and then it goes on to evaluate the expressions.
Can you do Clang with optimization? See what it does. Can you do Clang with optimizations and see what it does?
If Clang without optimizations did the right thing.
What do we mean by right thing there? I would have thought the
right thing is warn the user that he did something
that's
stupid.
Right. Yeah.
That's the right thing.
Yeah.
I often hear people to give the advice to get around undefined behavior by turning off optimizations, but this shows that
that's not a 100% solution either. Yeah,
optimizations still happen at 0 sometimes, right? And
I don't think this is an optimization problem. It's like all front end compiler front end thing, like how.
I would point out that previous versions of CLang would still warn, but they would print 25. So it's not something specific to GCC. CLang prefers to do it this way too. It just explicitly turned it off in this particular case.
So you were arguing that we have an opportunity to change the status quo because we don't have to worry about backward compatibility. But what requirement do we have to protect someone with an existing code base where, for example, auto vectorization can only turn on if the behavior is undefined? And if we define a behavior, it's going to block some optimization.
So I
have like 16x root.
I already answered that. I think that explicitly defined undefined behavior is the answer in all of those cases.
But that would require code changes, right? To add the annotation.
Yes, but yes. Yeah.
I was going to say that a lot of people depend on undefined behavior producing optimizations in their code. And so going to the committee and saying, hey, we want to take this previously undefined behavior, make it defined, we do frequently see pushback from people in the committee to say, look, this is going to mess up the performance of my huge fleet. It's going to do I don't know what. Now, sometimes it's overcome, that argument, but it's definitely present.
I accept that. I'm saying that even if all we did was limit to the extent by which the compiler is allowed to have the resulting machine language deviate from a naive reading of the source code, even if we did just that, because here's the thing: when you tell novices about undefined behavior or intermediates, doesn't matter. People who understand pointers, who understand the language, but haven't seen anything like this yet, and they say, "Yeah, obviously, if I'm dereferencing a null pointer, then obviously bad things will happen, right?" And it's the intuitive understanding of undefined behavior isn't wrong about bad things happen if you do this. It's about how bad those bad things can get. And so I think that any work in that, because it's one of those barriers of people saying, it's a cause of frustration that I considered myself a fairly advanced C++ user, okay? And during a personal project I did where I wrote all of the code from scratch, when I say all of the code, it's an operating system, all of the code. I ran into problems that took me waveform debugging, because that was an FPGA CPU, that ended up being either undefined behavior outright or undefined behavior adjacent. So it varies twice. And I'm saying, okay. And I had the tools to eventually look at where the problem is and say, oh, right. What happens if you don't have those tools? What if you just... So you find the engineers that probably knows. And that's how I know why everybody in the company ran into undefined behavior, because they came to me because they didn't have the tools to solve it. Yeah.
Two unrelated things. One thing I want to say is the answer to the pushback that David mentioned you get is a compiler flag, I think. If the standard changes, just have a compiler flag say, hey, treat this as undefined, and then it's up to the people to turn that on. The other thing I want to mention, not related to that...
We're not enough people for you to ask for permission. Just speak.
Wait, let me just finish the other thing I want to say. The other thing I wanted to say is that I think in a lot of the cases, not all of them, but a lot of the cases where we have undefined behavior, it could have been just an undefined result or like an indeterminate result. And I feel like we would have gotten the same optimization just without the craziness of your hard drive.
I'm with you. When people, I say to people, division by zero is undefined behavior, they say, fine, then give me some random junk.
Yeah.
Don't eliminate the whole function. So there's a difference between, because this inject poison into the intermediate representation. And I get it. With people optimization, it is difficult to control how far this will go. I get it. But I think we should make the effort. Yeah.
I just wanted to respond to the idea of just make it a compile flag. So compilers are completely free to add compile flags that do whatever they want to do with undefined behavior right now. Standardizing that, though, is fraught with difficulties, because now we create dialects of the language to where sometimes they behave this way and sometimes they behave this other way, depending on what compiler you use, depending on what flag you use. So there's a lot of pushback for dialecting the language. The one exception of that, which seems to be getting some steam, is the idea of profiles. So maybe you could turn on a profile for a particular module that you're creating, and that'll have the more defined undefined behavior.
So long as you don't break ABI, yeah.
So what I meant here was not that the standard standardize a compiler flag. What I meant is it define the undefined behavior to be what it thinks it should be, and then anybody who wants a different behavior can add their own compiler flag. But that flag is not in the standard or anything.
Let me just one more moment. Okay, first of all, I'll point out that that's the reason I have two separate bullets here, one for the language and one for the compilers. I just want to, yeah, that's not an interesting slide. Yeah, go on.
Sorry, one other way of looking at it is, does anyone know of a different programming language that's trying to move in this direction of having more undefined behavior? I don't know of any. I don't think anyone moving in this direction. Like this seems like this is clearly status quo bias, where we're just like, currently it is this way, and therefore people are defending.
But even in Rust, where they're like safety first,
yes.
And they do something I really liked, right? Where they say any integer overflow is not only undefined behavior, it's an assert. But if you compile in release, then it's undefined behavior. Because the assert allows the compiler to assume it never happens, and then it's undefined behavior if you remove that assert. So I think I really believe that undefined behavior to some extent are unavoidable in a language that wishes to be performant.
So the scariest words in the standard are ill-formed, no diagnostic required.
Yes.
That's a different category of that's a static property of the program, but it means that you didn't write C++, it was ill-formed, the compiler produced something. If you run that thing, it is undefined what happens.
Right.
And that's like any language, certainly any language which inherits the compilation and link model will have that, I think, because
to some extent.
Sometimes that's hard to get rid of because it involves solving the halting problem. So it's quite difficult.
That's going
to be something that we can't address with compiler.
I agree. One of the cases I had of a UB in my code, it's a personal project. I start from scratch, and when it gave me a linker error on memset, I just implemented memset. And then at some later point, I introduced the compiler library, and there were two definitions, and it's a violation of the one definition rule, but no linker error, and everything just ran but turned into an infinite loop. Do you know how long it takes to realize you're in an infinite loop when you're running at 1 hour per millisecond?
I have a suspicion that some people like undefined behavior a bit because it makes them feel smart. C and C++ people love, it's a little endorphin rush. Oh, no, that's undefined. That means...
Especially when it gets to I think we can have some empathy though for the standardizers and the implementers, because the conversation in this room today shows alone that just for one topic, like, it's not trivial. Like,
I think I said that explicitly.
I think you did.
Multiple times. I think that I'm not here saying we shouldn't have undefined behavior, or even I know how to remove this particular undefined behavior. Maybe division by 0. But just that the state of mind should view undefined behavior as a landmine waiting to explode. Please.
And I will just add that I think that most people that I talk to on the committee, they do see undefined behavior as a problem, and they are trying to plug these holes where they can, but there's always trade-offs, and they look at these trade-offs. I think the thing is just with the language, the way that it's set up, there's no way we're going to get to a point to where undefined behavior isn't like a serious problem, right? It's always going to be a problem for this language. There's no way that we can solve it.
That's why that slide also talked about compiler implementers, because my plea isn't only for language designers, it's also for the compiler implementers.
I take that it can never be solved, but I think it could be less bad.
It could be a little bit less bad, and that's what we're doing in the committees. Make it a little bit less bad. If you want to have something seriously better, you're going to have to switch to Rust or some other language that we thought about at the beginning.
Talking about Rust, I mean, they're trying this, right? To really make sure that nothing, or at least a very minimum, is undefined, but at the same time, they're providing a evil twin to the language where you declare code unsafe, because there's like, okay, I'm not going to be able to do everything I need to do if I'm getting into that straitjacket.
And not only that, take my memset example from before.
Yep.
That's not on the compiler. That's obviously on me. A linker error saying, two implementations of memset exist would be nice, but the way linking in Linux works, where static library, because this is a static library, the first one to appear on the command line takes precedent, that's also not possible. So I understand why it came to, but I still spent a day and a half on it. I'm allowed to be a little pissed off.
Well, the devirtualization optimization. I hadn't seen that before. That was great. What's the point of that? Like,
That's the only way to optimize. Otherwise, you saw what happened when you tried to define
but
what the compiler.
If I've got a function pointer that can only ever point to one function, why don't I just fix that as a programmer?
Because it might be under like a constant condition somewhere, like pounded or like a context for a variable. That you
By the way, our time is up. We are into a break time. I'm fine with it if you are.
I think we should I would add, there wasn't one possible value. There was two possible values for the pointer.
Yeah.
But the compiler said that it discards the null pointer option.
My personal opinion about this, and it's a bit unpopular, is that the purpose of a debugger, of an optimizer, is to allow you to write more maintainable code. So before optimizer were around, you had to think about what the implementation will do. And here you write the best design you have for the program, and you trust the optimizer to turn that into performant code.
Yeah.